So I think a chunk of you were here for the earlier talk. If you weren't, that's okay, because this talk can stand by itself as well. So whereas my previous talk was really going broad, looking at what are the core principles of building microservices, this talk is actually looking in more detail at techniques around testing and deploying those services. We're going to talk a bit more about technology. We're going to go a bit deeper into the operational side of this stuff. Some of you may have seen a blog post by Uncle Bob. He's around non-political things. He's quite sensible most of the time. But there was a blog post he put out recently where he stated that with microservices, all this operational stuff, all this stuff around deployment is just an implementation detail you don't need to worry about. I actually disagree, because I think it's only by understanding how our services are going to be deployed that we can actually really think differently about how we model them in the first place. I think with a monolithic architecture, in many ways, the infrastructure, how we deploy our applications can be an implementation detail. I don't think that is the case with microservices, at least not until we have those platforms as a service that really do abstract ourselves away from all of the detail. And I think they're probably still 5 years away. I said that 5 years ago as well, by the way, so they're not here yet. So again, as you were here, if you were here before the break, when we think about what microservices are, we're thinking about this small autonomous services that work together. And as I mentioned, one of the key characteristics we need to ensure we have of our microservices is that for them to retain their autonomy, they need to be independently releasable. I need to be able to make a change to a single service and deploy that without it breaking or affecting anyone else. And under that banner, there are two sort of related topics we're going to go into some detail on now around testing and deployment. But we're going to start, helpfully, with at the beginning around deployment, because it's harder for us to test an application that we haven't actually deployed yet. And so let's think about one of the basics we need to consider straight away. We have a service. Where do I deploy that? We have sort of two competing models. One says we'll deploy a service onto a host. One service per host. That host could be virtual, it could be physical, but we're talking about some level of operating system isolation. Or we have another model where we have multiple services per host. Now, I actually have to say I prefer and strongly suggest you adopt this model if you can, but it's not always that clear cut. So what are the different trade-offs that are going to push you one way or another? The reason I like the one service per host model is that it's much easier to reason about. It's simpler. And you know what? Microservices add enough complexity as it is without us adding more complexity in the infrastructure. It's very easy to reason about. If you think about why it's easier to reason about, if I deprovision a machine, I know which service is affected. If on that host, the CPU is pegged at 100%, I know what service is impacted and probably what service is to blame. Provisioning becomes potentially easier as well. We actually keep ourselves open to many different solutions, because now I can think about provisioning my service and my host at the same time, because they're not separate. So effectively, I can tie the life cycles of these two things together. I can't do that in this model where multiple services are being deployed onto the same host. I have far fewer side effects. If any of you have ever had the problem of deploying lots of, say, services behind the same IIS instance or into the same servlet container, you'll know that sometimes one service can impact another service. There was the mythical unified class loader that JBoss had until about JBoss 4, where it would just randomly pick up classes from the other JVM, the other programs, which is just hilarious to me. But again, one service misbehaving in this world could take out all the other services on that machine. It can't happen if I've got a level of resource isolation by having a separate host. It also actually enforces interdependence. It really keeps you honest about keeping these things truly separate. I've seen people in this world get away with making lots of very fine-grained chatty calls locally to other services on the same machine. So they haven't actually properly decoupled the services, but they just don't notice because they've just wedged them all on the same box. But why is the model on the right often attractive? Why do well, some people like having lots of services on one host and one level of isolation? The first actually is from a host management point of view, so actually managing the underlying machine that it lives on, it can be simpler. If you're in a world where this is being done manually, and your hosts are snowflakes that are carefully nurtured and looked after over many, many months, you're not going to want to have to build up loads of new ones all the time to support this sort of deployment model. Also, this model can be cheaper. I mean, like financially cheaper. Like it can be less expensive, like dollar amounts less expensive. We'll talk about why in a moment. But first, let's talk about what could we do to solve this problem. How could we reduce the host management costs in this part of the world? So one of the key things you want to look for, if you can, is the ability to provision hosts using an API. I want to be able to write some code and have it bring up or tear down a machine. So it doesn't have to be an Amazon or a DigitalOcean. There are plenty of platforms that you can run in your own infrastructure that allow this to happen. You can use performant, for example. It's even possible with VMware. If all these virtualization platforms that allow us to happen, I can use libvirt to control Zen and KVM instances and run code to actually bring these machines up and bring those machines down. That allows you to say, okay, well, running a machine, configure a machine by hand, now I've got a script that configures one machine and it runs automatically. If I need to do 10 of those, that's a for loop. I'm sort of reducing that sort of linear growth of work by automation. Neil Ford says that, he points out that we, human beings, are very, very bad at doing the same thing over and over again reliably. We forget things, we make mistakes as we do it. That's why manual testing is so error-prone and depressing as well. It says when human beings try sitting there and doing the same thing over and over again, all the computers go to the pub and take the mickey out of them. Because it turns out computers are excellent at doing the same thing over and over again. It's what they're designed for. So when you're thinking about keeping that host management overhead, you need to be looking towards automation. So bringing up hosts, configuring those hosts using scripts. And if you just look at the host side of this, the virtualization platforms out there, all of them support some form of API provisioning. All of these systems do. The challenge is often, do the people that look after this stuff in your own infrastructure let you get hold of this? Sometimes you can run things on top of, say, a VMware instance that give you increased levels of isolation. We'll talk about a bit about that in a moment. So to think of the normal workflow we might have around automating our host provisioning. We run some code and up comes the host. So we have now something we can log into. We might be remote desktoping into a Windows machine if we're a glutton for punishment, or maybe we've got Windows remoting. Or in the Linux world, we're SSHing into a box, whatever that might be. And then we configure that host. We install the dependencies we might need. We deploy the version of .NET we need. We deploy the JVM we need to run our service. Maybe we deploy a specific version of Apache. And then we install our service on top of that. Fairly straightforward. So maybe we're using an infrastructure automation tool to do these last two steps. And all those tools, the Ansibles, the Puppets, the Chefs, allow you to, are designed to be declarative. So you make a statement about how a node should look. On this machine, on this host, here are the things I want to be installed. And if those things are already installed, the script does nothing. And if they're not, it makes it happen. It'll even downgrade versions of things if you've got newer versions of them. That's good, right? That's a useful thing. And that is to allow us to run those same scripts over and over again on the same machine and achieve the same results. As we get this cycle going on, bring up the host, and we configure it, we install the service, new service version comes out, we reconfigure the host in case any of our dependencies have changed, and then deploy our software again. The problem is this can sometimes take a lot of time. Installing a new JVM, say, on an Amazon machine, because by default, the Amazon instances, the Amazon operating system, CentOS and all those, they'll include the Open JDK. They won't include, Oracle's JDK. And certainly for Java 6 apps, that was always a bit hairy. So the first thing you have to do is actually go and get the Java VM, the JDK from Sun. Wow, those are the days. Oracle. And you'd host it locally to try and make it faster, but it could still take 4 or 5 minutes to fetch and install, let alone updating all your other packages, installing the right version of Apache. And so it might take you a few minutes to bring up a machine, and then you're sitting there waiting for 5, 10, 15 minutes for all of your software to install. And you're doing that every single time you launch a node, every single time you configure it, and that starts getting old, because when you think about it, when you launch a machine, launch a host on one of these platforms, there's already software running on it. There is already stuff there. So how does that stuff get there? The answer is that you can, with all these virtualization platforms, you can create custom images. You can create images that already have software installed. That's how the images are created in the first place. And so these platforms give you different APIs and tools to work with. There's actually now a tool called Packer, which comes from the same guys that did Vagrant. It's the HashiCorp guys. And it gives you an abstraction layer over creating custom images for different platforms. And so rather than, say, having to deal directly with the VMware tools or directly with the Amazon tools, you can use Packer instead. One of the nice things is that it actually supports your configuration scripts. So let's think about what standard virtualization looks like, and then we'll think about how Packer works within that. With standard virtualization, I have some underlying physical machine. This is actually what's called type 2 virtualization. So type 2 virtualization runs on top of an operating system. I've got my base operating system here. So this could be a Windows machine if I'm going to run Windows VMs, or it could be Linux if I'm going to, say, run Linux VMs. I then got a hypervisor. The job of the hypervisor is to map from virtual resources to physical resources. It's to sort of control how much of the computing resources a virtual machine can see. It also handles security to stop things, something coming out from one of those virtual machines and hitting the base operating system or other VMs. It also handles things like networking. And then on top of that, I have a virtual machine on which I can now run another full-fledged operating system, and then I can put my apps, my service on top. This is a stack diagram. And that thing there, when you create a custom image, you're creating that whole bundle together. So our Packer image in this world would be one of those things. And so Packer lets us create those as a binary artifact and spin them up on any virtualization platform we like. And we'll come back to this diagram in a minute, because this is important when we think about the cost of virtualization. So if you've already in the world where you're using one of these tools to configure a machine, with Packer, you can use that as part of the Packer tool chain to create the image. And so you could use that to create an image for AWS, create an image for DigitalOcean, even for OpenStack, and also really helpfully for Vagrant. So Vagrant is a great tool for running effectively a cloud on your box. If you want to run production-like virtual machines in an easy way, Vagrant's an excellent tool for that. So maybe you're developing on Mac, maybe you're developing on Windows, but you're going into production on CentOS 7. You can run a CentOS 7 virtual machine on your laptop and actually deploy your services on it. And Packer will create those custom images for you. So what we do here is as part of the image creation, that's where we install all of our dependencies. It's where we install the right JDK, the right version of Apache. But of course, why stop there? Why not actually put our service on there as well? And so that when we launch the machine, our service is running out of the box with all of its dependencies, just ready to go. This is a great pattern for implementing something called immutable servers. We'll talk about in a moment. It also gives you very, very fast spin-up time. Once a virtual machine is running, your service is running, rather than waiting around for 10, 15, 20 minutes to install all of your dependencies. This is exactly why Amazon use custom AMIs. In fact, if you're on Amazon and want to use auto-scaling, as your AMIs are brought up, they have to have your running application on them. This also can give you some level of provider agnosticism, but also abstracts you as well from the underlying technology used to build the service. So if I'm just launching an image, I don't know whether or not the service running on that box was written in Node.js or written in Java or written in C#. I don't care. I launch the image and up it comes. And if I'm just creating images, then I'm actually I can use the same scripts to create an image that works on Vagrant or VMware or AWS. So it actually allows you in a more hybrid environment to have some level of portability. Although I would say the VMware support on Packer is a little bit dodgy. There are some downsides to this approach, though, of baking everything into these custom images. One of them is that feedback can suffer. If the only way to bring up a running application is to create a custom image and then launch it, that's a problem, because it could take, that 15-minute time it could take before custom images, you're now doing that as part of the build of the image in the first place. You're doing it once and once only, but even so, if that's the only way you can bring up a new version of your software, that's going to kill productivity. So you do need a way to be able to launch your application anyway. And also cycle time can be a challenge, especially when we're talking about, say, patches, like operating system patches. So if my production environment consists of lots of machines running these custom images, and I need to push out a patch to fix, say, the shell-shocked bug that happened recently. Now, if I'm using a system where I can just run Puppet or Chef or Ansible again on those boxes to install the patch, that could be quite a quick operation. But if I have to build custom images and put them out, that could take longer. That's a trade-off to think about. One pattern this enables is this thing I talked about of immutable servers. So if you have all of your scripts in source control that tell you how this box is configured, that's great. You get visibility, you get traceability. It's repeatable as well. When I run these scripts, I get a node that works that looks like this. But if you give people the ability to make further changes on that box that are not in version control, then you have what's called configuration drift. What's in source control is not the reality, it's not the state of production. You get a production defect, you try and reproduce it and you can't. So maybe you let people SSH onto the box, and people have been going on there and they've been manually installing patches. Maybe they've been manually fixing configuration files. And this problem of configuration drift can kill your repeatability of the builds. And so with the immutable servers, you say, if you want to make any change to this box, you've got to destroy it and recreate it. And so the last stage of creating an immutable server could be to disable any remote access. Now, obviously, if I can't even log on to the machine, I need to get the information off. And that comes back to stuff we talked about before the break. If you treat these things as truly stateless, you need to be getting all of your metrics off of that machine. You need to be getting all of your logs off of that machine as well. And so that's a really kind of a safe pattern. A lot of organizations that start with Puppet and Chef, where they run them over and over again on these sort of semi-permanent servers, move to this model if they're on the right platform. What about one of those other downsides we talked about earlier? So why is it sometimes cheaper to run multiple services on a single host? So what is the cost? Why is it expensive to have lots of small hosts lying around that line up to my service boundaries? Remember our stack diagram from earlier? We were looking at this type 2 virtualization. We have this hypervisor, and that's doing a lot of things. it's, as I say, security, mapping resources, kind of isolating resources from each other. And we also have this full fat operating system up there. This is a full operating system with its own kernel running there as well. And this is really what's expensive. As we add additional virtual machines, even if we make them rather small, the overhead of the operating system is more or less fixed. If I'm just pulling out lots of different Ubuntu instances, that's still completely new Ubuntu kernel and everything else running. That takes resources away from the underlying machine. Likewise, the more virtual machines you've got, the more work the hypervisor itself is going to have to do. I should think of this like a sock drawer. I've got a sock drawer and I've got socks in it, but it's a bit chaotic and I can't always find things. So I think I know, I'm going to put dividers in my sock drawer. So I go down to my workshop and I cut some pieces of wood and I put the wood in the box. And so now it's much more organized. I can keep blue socks in one section and red socks in another and decide, oh, that one, I'm not going to put socks in, I'm going to put t-shirts in it. It's great. So it's much more organized. It's much more flexible with some isolation. The socks, the blue socks and the red socks don't mix. But I've got less space overall. The dividers themselves take up space. And in the same way, with this virtualization, these take an overhead. And so the more virtual machines you pack onto the same system, the higher proportion overall of your overall resources are going to the hypervisor and the virtual machine overhead. And so you get diminishing returns. And that's often why we can't just pack in lots of small virtual machines. There is an alternative approach that's come out of the Linux space, actually the BSD space, and Oracle, Solaris is where this stuff really started. And that's the idea of actually, rather than having completely, is to use the kernel itself down here to do the isolation between different sort of process spaces. And that's where LXC came from. So LXC, until recently, was the most popular container implementation. It's probably still the most widely used container implementation. And so you think one of the things a kernel does is it manages processes, and it makes sure that a process of one user can't see the processes of another user. And it manages those things as trees. And so containers, in many ways, just take that and extend that idea throughout. With container virtualization, we have our machine, we have our base operating system, and we have a container, and it looks quite similar at the moment. But firstly, there's no hypervisor in the mix. There's actually a kernel in the base operating system that is taking over the job of the hypervisor. Secondly, these operating systems here, they can be different operating system distributions, but they have to share the same kernel. So I could run CentOS 7 and a different version of Ubuntu here as long as they're okay using the same kernel underneath. So already I've reduced the overhead in having separate kernels. I'm not running as full-fledged operating systems in there, and that's drastically reduced the overhead that I've got. There are some other benefits of these container approaches. Virtual machines can take 2, 3, 4, 5 minutes to spin up, depending on the underlying platform. I've seen it take as long as 20. Containers take 2, 3 seconds to spin up. You can clone them rapidly. They've got things like copy on write file system support. So you can bringing them up and tearing them down is very, very fast. You also have much more fine-grained control over your resources than you do with a normal hypervisor. There are some downsides. At the moment, this is Linux only, although I think in the next version of Windows Server that will change. You are constrained to using the same kernel. So if you do need to run different kernels, you'll have to use their type 2 virtualizer. So you've got very fine-grained control, very fast to provision. One thing I should say, too many transitions. These things are not as secure as, in general, as full fat virtual machines. And they don't necessarily promise to. They're trying to close all those loopholes. But there are exploits where things running here can bust out onto the host operating system. So just be aware that this is not a great model for running untrusted code. So if you are running untrusted code, you either need to use full-fat virtualized machines or separate physical machines, Or there are some container-based technologies that do isolation better. So OpenVZ, for example, is much better isolation from a security point of view, but does require custom kernels, and it's not as widely used. And so, of course, in this world of containers, this is great, but containers actually have some shortcomings. They don't do anything around networking for you. So working out how to route traffic from the outside world onto the containers that are living on that machine is somewhat challenging. You end up doing all kinds of IP tables, port forwarding on the machine. They also don't give you any tools around managing those containers themselves. You're sort of building them themselves. There's no unit of abstraction like an image like there is with, say, the virtualization platforms we looked at. And that's really what Docker gives you. So Docker gives you an API to control and configure containers. Originally, it was just using LXC under the hood, but they decided to, as of 0.9, implement their own container technology. It handles the networking for you as well. So it handles routing to the container running on a box. It also gives us the unit of abstraction we're missing in the shape of the concept of an image within that container, which is like a Docker app. So we have our machine, our base operating system, we're running Docker as a process on top, and we're sort of running apps on top. Technically, we can still run our own operating system distro within our containers, but in practice, people don't tend to do that. Now, the things we deploy are actually stored in an image registry, so you can actually connect to public Docker image registries, you can run your own. And this just works like you might run your own, say, Chocolatey repository or Debian or Red Hat repo in your own organization. It's the same idea. And so if you're using, if you're producing Docker apps as part of your CI build, this is where they'd live. And then you use the Docker APIs to install versions onto an instance. It gives you good power to do things like deploying given versions. It can even do smart things like it'll only copy the bytes that are the difference between version 1 and version 2. That makes the copying process much faster. And so it makes it easier to rubber stamp these things out. It also supports things like data volumes. So if I want to run a database, databases are stateful. Well, actually, they're not, right? The database process itself isn't stateful. It's its data directory. So it allows me to say, OK, I'm going to run a database in one application here. And its data volume is actually going to be stored as another thing on top of Docker. And so then I can tear down the database load and redeploy it, but I can keep my data volume around. And then I can actually clone it. It's very similar to sort of how elastic block store devices work on Amazon, if you've ever used those. Now, obviously, this is great. And there are other companies, a lot of other companies working in this space. CoreOS have built an operating system where they said, well, containers are a great idea. Let's just make our unit of our package concept on our operating system Docker apps. So rather than Ubuntu or rather than RPMs, rather than Debs, it's going to be a Docker app. Their operating system is actually stripped quite bare to only run Docker, which actually means you're freeing up more resources. It's not trying to do anything else. Recently, they've actually come out and said that they're worried about the direction Docker is running in. They're also coming out, like both Docker started off as just handling this part of the problem, and CoreOS came to handle how do you handle lots of Docker instances. And now Docker's moved into their space, and then CoreOS have come out and said, A, we're worried about this, and B, we're worried about some of the implementation of Docker. So they've come out with their own specification called Rocket. It'll be interesting to see what happens over the next couple of years. I think containers are here to stay. Docker's definitely got the energy right now. Be interesting to see where that goes. Now, Docker by itself does not give you an Amazon on your infrastructure, because this solves running containers on one given node. What's missing here is the concept of a scheduling layer. So when you go to Amazon and say, launch me a quadruple large instance, launch me a T2 micro, Amazon behind the scenes is looking around saying, OK, where can I find, that machine's got space. Here you go. I'll provision it, and here's the link back. So but out of the box, vanilla Docker doesn't do any of that part for you. It handles how do I manage a single host running Docker. And so that's where you need other tools on top to give you that scheduling layer, or you do it yourself. One of the nice things is I mentioned Packer earlier, so Packer can create these images for me. Packer can also create me Docker images too. So that's quite nice from a transition point of view. I've been using maybe creating custom images, maybe using Ansible or whatever else, and I want to give Docker a go. Well, I'll use Packer to create that Docker image instead. That could be an alternative artifact for me. So some people I know use Docker just for dev and test. I can run a lot more containers on my laptop using boot to Docker than I can run virtual machines on my laptop using Vagrant. So if you're bringing up lots of microservices, it's a very viable approach to run a Docker instance here and just deploy that locally. And so if you've got one tool chain that can kind of create, maybe a custom image for my production deployments, but a Docker app for dev and test, that works quite nicely. And so we've always got this progression from semi-permanent servers to image-based deployments, and then Docker, this sort of and containerization. I kind of think that the competition in the containerization space is going to make make what's happening in JavaScript look like a mild, disagreement. This is going to be a very, very hot space. The great thing is we're going to be the winners. Unless any of you are out there trying to sell technology or backing these companies, I think if you're using the technology, we're all going to win. Other tools in this space, I really like Terraform, which is also from HashiCorp. It goes beyond saying how do I configure an individual node, talks really about how do I declaratively provision entire environments. Early days yet, but the 0.3 release seems pretty stable, and we're using it in a couple of places and quite like it. It's worth taking a look at because there's some very powerful stuff. You've also got other stuff being built on top of Docker. You've got Dees, which is actually giving you a platform as a service. It's trying to it gives you an Heroku-like looking API running on top of Docker instances, which could be really powerful because Heroku is awesome, but it doesn't run on my machine. So that's often a challenge for some of the clients I work with. And obviously, there's been a lot of hype around this thing, which I never know how to pronounce, which is Google's technology for handling that scheduling layer that they've open sourced. They used it internally working with their own container technology. There are other tools in that scheduling space. CoreOS have got their own clustering technology. Interestingly, the first people to get Kubernetes up and running were Microsoft. They support Docker on Azure. And they beat Google to the punch on that one. Google also provide hosting of containers now. Docker have bought Orchard, who do the same thing. And the Amazon Container Service, I'm especially excited about as an Amazon fanboy. Dislike the morals and how that company is run. Really like their products. So I'm looking forward to the Amazon Container Service as well. Okay, so now we thought about how we deploy our applications. Now, how do we actually make sure they work? It's this world of testing. So this is sort of a very, hopefully by now, how many of you have seen this picture before? A few? Oh, that's great. I'm glad it's like less than half the room because I can talk about it, right? This is Mike Cohn's test pyramid. It's one of the most useful mental models I've ever had in terms of thinking about automated testing. At the top of the pyramid, we have very broad scope tests that touch a large amount of functionality. At the bottom of the pyramid, we have things that test small amounts of functionality. The idea is, as we go up the pyramid, when we increase the scope, we get more confidence. If a test up here that tests, say, from a user interface all the way through the system and back passes, I feel pretty good that the system works. A unit test passing, I don't really know the system works. I know that one function works. As we come down the pyramid, our tests become much faster. We get really good fast feedback from a unit test, right? We also get better isolation. And that means down here, when a test fails, we know which piece of functionality is broken, because by definition, we're testing a small scope. The top of the pyramid, if a test fails, we don't really know often what caused the break. And the idea behind the pyramid is you roughly want a lot, almost say an order of magnitude more unit tests and service tests, where we're testing services in isolation, and an order of magnitude more service tests than user interface tests. So this is from Mike Cohn's book, Succeeding in Agile. So, let's imagine I've got a monolithic system, and I'm doing some unit tests. And so they would just be like little isolated tests, maybe just testing methods or functions. Then got my service tests. And my service tests, I'm really testing the thing in isolation. Maybe I'm testing a few groups of functionality, maybe just parts of my system together. But the key thing is I'm testing a service or a piece of code independent of any other relationships to the outside world. And then with the UI test, I'm actually bringing up, I'm actually running a test across the user interface or putting something on a message bus and seeing it flow through. When we think about microservices, let's think about how those different types of tests might apply. So I've got my inventory service down here. And I'm going to change my inventory service. And I want to release it, because I want to have independent release ability of this stuff. What do I need to do? What tests do I need to run to be confident that I haven't broken my downstream or upstream services? In terms of my downstream services, we normally want to test like this. I'd take my service, I'd swap out the downstream service, bring up a stub or a mock. I'd run some tests against inventory and confirm that I work how I expect to work with my downstream service. I've isolated myself. I get good isolation, so I'm only testing myself and not the whole rest of the world. There's a tool called Mountbank that does a nice job of actually creating stubs for web services. It can actually stub multiple points. It's like a little software appliance you program over an API, and it can stub multiple different ports. It's written by a coworker. And that's actually fairly straightforward, that world. I bring up the service by itself, stub out my collaborators, run some local tests. The world is good. The problem, of course, is here. How do I know when I deploy inventory that I haven't broken shipping, the upstream service? This is a consumer. It has expectations of me. Have I met those expectations when I go live? Normally, we would deploy these two things together in some kind of end-to-end test. Right, we bring them all up, and then run a test across the whole system. This becomes challenging, though, when we start thinking about the number of moving parts in a microservice system. Because just how many of these different scopes of scenarios am I going to have? How many different end-to-end tests am I going to need to test all these sorts of interactions? End-to-end tests like this are problematic for a number of reasons. Browsers. If you're using browsers to drive your tests, browsers can and will crash for no apparent reason that often has nothing to do whatsoever with your functionality. So you get false negatives. Timing. AJAX calls in your application layer, they sometimes just don't converge how you think, and you'll get a false negative. Provisioning environments can be slow. Networks are unreliable, so sometimes things will fail. Again, it's got nothing to do with your application. Deployment will often fail if you've got lots of machines you're bringing up. And diagnosing the failure of these large scope tests is difficult. Remember, as we talked about before the break, we have increased our surface area of failure with running microservices, and now we're trying to run end-to-end tests over them as well. So this is fraught. The false negative, the flaky, non-deterministic tests are often rife in this area. And so at scale, these things break down. So is there a way for me to catch breaking changes without having to run an end-to-end test? Well, of course there is, because that's what I've led up to it. And that's what we call consumer-driven contracts. So these are all about conversation, communication, and trust. This is how this stuff works. Here, the shipping service, our upstream service, calls inventory service the service that we want to change. Now, hopefully, we've had a conversation about this API, but however it's happened, the shipping service, as a consumer, has expectations about how the inventory service is going to act. It thinks, when I call this method, I expect you to do this. So we've had a conversation, or there's a contract's been drawn up, or something's happened. And with consumer-driven testing, what we're doing is we take those expectations and we make them executable. So we make them a test. And that should be written ideally by the consumer, and at the bare minimum from the point of view of the consumer. So maybe you pair, maybe they write them and give you the tests. Those tests then run in your CI build, in your CD build. And so every time the inventory service builds and runs its test, it runs the test of all the consumers. And those tests can be run in isolation. And so if one of those consumer tests breaks, you know, this version of my software is going to break shipping. I need to go talk to the shipping service people. I can't deploy, so I'm going to break them. We may have legitimately introduced a non-backwards compatible change, or it might be a bug. There's a tool called Pact that does this. It's an open source tool, originally written in Ruby, but there are now ports for Java and .NET. Again, this came out of REA. One of the ways it works is you, as the consumer, use the DSL. So you write maybe a test in Ruby using the Pact DSL. You then run those tests against a local Pact stub. And that generates, as an output, a JSON file that's a specification of your expectations. And it's that JSON file that the producer then runs against their service as part of their builds. And by having the JSON specification, it means that you can have, you know, a Java Pact client and a Ruby server, and they can share that JSON file as an artifact. Beth Scurry, who runs this, she's also created this Pact broker where you can store the different Pact versions. So you might have multiple different versions of a consumer out there, and so you can actually run over all of those sorts of tests and say, am I going to break any of them when I go live? So this is actually a concrete implementation of this idea. So, no integration tests? Well, not quite. Integration tests are still useful, but you probably want a very small number of them. Don't think tests, think journeys. What are the core journeys in your system? Buying a CD, signing up as a user. You've probably got 5 core journeys. So maybe if you're going to have end-to-end tests, just have 5, a very small number of them, not loads. But I'm going to hold you up a little bit, because when we think about testing, we think about activities that we do before we go into production. And then there's a yawning chasm of doom, and then we hit production. And in the world, and over here, we do something called monitoring and alerting. So in this world, we have testers or developers who create tests using one set of tools. And over here, we have production people who have a completely separate set of tools. We're trying to validate, does my system work here? But we're trying to validate, does it work before production? And then we're trying to validate, does my system work after production? And yet we use different tools, different processes, different people who often don't talk to each other, which always has struck me as being very odd. And in reality, we seem to do this. We spend a large amount of our time trying to remove the chance of there being any failure before we hit production, and give very little thought to how do you validate that after. At REA, they don't do integration testing. They go straight into production. They actually go to their QA environment after, so then they can diagnose failures if they need to. But they can only do that because they have a strong culture of monitoring and remediation. They spent some time understanding we can catch defects in production well. Because the more complicated your system becomes, the more you're going to get emergent behavior in production. The harder it's going to be for you to reproduce every given test case before you release. And it's not necessarily a zero-sum game, but certainly as you go from the monolithic system to the more distributed system, I think your focus is at the very least going to have to broaden. This is something you're going to have to think about a lot. And if you've got these end-to-end journey tests that we talked about, that test a large stroke of functionality through your system, why not run them in production? Why not use those same tools? Have Nagios order a CD every 10 minutes. This process of injecting sort of a fake message into your system or a fake transaction is called synthetic transactions. I've done this before with trading in a bank. We'd fire off this trade, and every 5 minutes or so, we'd fire it off every 5 minutes, but expect to see a result in under 10 seconds. And so we're actually monitoring the semantic behavior of our system. It's called semantic monitoring. So I don't care anymore, is the CPU of one of my machines at 100%? That tells me nothing about whether or not my system works. Whether or not my system works is, can I buy a CD? Can I sign up as a new user? Do that in production. Find a way, though, to make it non-destructive. So when I was doing the banking work, the trades we were pricing in this way went into a back-end, into a book that no one ever booked into the back-end systems. I spoke to a company in Germany who had the misfortune to run their tests against their production fulfillment systems. And they ordered 200 washing machines to be delivered to head office. And they only found out this was a problem after the first truck had arrived at head office and the second one was being filled up. So if you are going to take this idea of synthetic transactions to do semantic monitoring, just make sure you find a way of making it non-destructive. But it is a way of taking that tool chain from the pre-production validation world and taking it into the post-production world as well. So just to summarize, when you're thinking about deployment, try and move to a one service per host model. It is simpler. You will thank me. Getting there can be painful, but once you are there, it's a much better place. And once you're there, you can start thinking about things like image-based deployments, or maybe containerization, maybe via Docker. And then also, you should strongly consider this immutable server pattern, because it makes, again, your system much simpler to reason about. And when you're thinking about testing, we need to get away from this idea that testing is just what happens before production. Testing, we've got really pre-release validation. That's normally what we talk about testing. Isolated service tests, journey tests, consumer-driven contracts we talked about. But then when we're thinking about validating after release as well, we can also use testing there with things like semantic monitoring. And so we need to think a bit more holistically about our systems. I will send around links to all of these slides, probably via Twitter, either later today or tomorrow morning. So I am working on a book on this subject. I said there would be a discount code if anyone wants to buy it. It's in early access at the moment. You get a DRM-free copy on the ebook. It should be in print in, February. The code's for you guys in the room, so don't go putting it on the Twitters. Thank you. But they are. I hope you will enjoy that book. And if you do read it, please do send me feedback, positive, negative, or otherwise. There's also, I've got some other talks around these subjects that's up on my Lanyard profile. There's a talk there called From Macro to Micro, where I talk about how you break apart databases, amongst other things. I know someone was asking about that earlier. So there's a bunch of other talks up there. So I want to say thank you for your time. I've gone a little bit longer than I hoped. I was hoping to have more time for questions. But I think we've got 2 minutes for questions. 2 minutes. Question?
So you mentioned about the downsides of having end-to-end tests with microservice architecture. Does it mean that with microservices architecture we can apply acceptance tests with development and automated acceptance tests and all?
I think it's a scope problem. The more services you have, the more the complexity of those tests increase to the point where they become counterproductive. So when you've got 2 or 3 or 4 services, that's probably fine. Maybe you can still do integrated tests, end-to-end acceptance tests there. But if I've got 450, like at Guild, I'm not going to be running acceptance tests across that whole scope. So when we talked in the last section about this idea of these banded contexts that nest, well, maybe I've got an acceptance test around this cluster of services here or this cluster here. If I'm a team and I own services, I might own 2 or 3 or 4 services in the same part of the domain. I might choose to have an acceptance test there. But whether or not I've got an acceptance test that covers the whole scope of my system anymore, I think that's somewhat more debatable. But I don't think you throw them away straight away. I think what will happen is, as we talked before as well, you start off with a small number of services that will gradually increase and you may get that hockey stick. You will find the point along that journey where these things stop making sense. Now, I think what you should be doing is bringing in consumer-driven tests before then, and so you're ready to go into another mode. But I think it's a gradual, you'll have to move away from them over time. So I don't know anyone at scale that's doing them across everything. They'll find smaller bulkheads to do them on. I am actually over time, so I am very sorry for that. I am on Twitter. I will be back at the second coffee break. I'm being whisked off to see Kiev, which I'm really looking forward to, but I will be back in the afternoon. I'm on the Twitter. I do respond. And if you are interested in a job, I don't know what the work permit situation is like going from the Ukraine to Germany, Italy, Turkey, or the UK. But we could find out together, so do ping me afterwards. But thank you very much for your time.